Good day, I'm Norman Wildberger. Today we're going to look at the prettiest theorem in calculus, which is a theorem about cubic curves, or cubic polynomials. This is one of a series of foundational lectures in mathematics where I'm trying to establish proper logical foundations for the subject. And in the last few videos we've been talking about calculus in a very elementary setting, the setting of polynomials. So it turns out that we can do calculus this way purely algebraically without any notions of limits, without any notions of real numbers, and complete precision of thought. We're now going to reap the rewards by studying this beautiful theorem. So cubics, or cubic polynomial, is something like this. As a polynumber, it's just a list of 4 numbers. The 4 numbers are the coefficients of the polynomial when it's written this way in standard alpha form. So this polynomial is of degree 3 if this coefficient d is not equal to 0, and we'll assume that from now on. Then it's called a cubic polynomial. Now when we graph such a polynomial, in other words, what we do is we plot points of the form, say x coordinate r and y coordinate p of r, where p of r is what you get when you replace alpha here with the number r. If you plot all those points, then you get a curve that looks something like this, perhaps sort of like this, or maybe going up and down like this, or maybe like this. So now the study of these cubic polynomials and their graphs, so we're talking about what are usually called functions of this kind. This is part of a larger study of cubic curves, where we consider more general kind of equations involving, say, x and y, polynomial equations where the total degree is 3. These cubic curves were studied by Descartes, by Newton. They were of interest to almost all classical mathematicians because there's a lot of really interesting things that turn out to happen for cubic curves. So today we're going to talk about a very special kind of cubic curves, these cubic polynomials. So it's important to realize that there's a much bigger, more general theory of which what I'm going to say to you now is only a small part. So our strategy is to review calculus in this elementary setting in the context of cubic polynomials. So you'll see exactly the steps that we need to go through to establish the foundations of calculus for cubic polynomials, and then we'll be able to state and prove this most pretty theorem. In fact, we'll be able to do that all on one page. So our strategy is to, first of all, establish some of the basic calculus constructions for a cubic polynomial. So we're going to start with a general cubic polynomial, a plus b alpha plus c alpha squared plus d alpha cubed. And we're going to compute various things for it. We're going to compute the Taylor polynumber or Taylor bipolynumber. We're going to compute the derivative and various higher subderivatives. And then we're going to find the tangent polynomials or tangent polynumbers for this thing. Geometrically, that means we're going to be studying a curve something like this perhaps. This is the particular polynomial 5 minus 3x minus 4x squared plus x cubed. And then say at the point r equals 1, the tangent line ends up looking something like this, and the tangent conic is a parabola looking something like this. So we want to be able to compute for every value of r what the tangent line looks like, what the tangent conic looks like. And our theorem is going to be something about the tangent conics. Alright, so the first order of business is to find the Taylor polynumber for p. That, by definition, is just p of alpha plus beta. We replace the alphas with alpha plus beta. And then we expand that using the binomial theorem here and here. And then we collect terms. The terms not involving beta, the terms involving beta, the terms involving beta squared, and the term just involving beta cubed. So it's just a question of expanding these binomial things out and putting it all together. Now these three coefficients that are appearing here, actually there's four of them including that one, these are the first subderivatives of the polynumber we started with. So this thing here is d0 of p. This one is d1 of p, or the derivative of p. This thing is d2 of p, and this constant d is d3 of p. d1 of p is just the same as the derivative. So this is the derivative of that. That's how we define what the derivative is. The derivative is the coefficient of beta in the Taylor polynumber. But at the same time, we also define the second subderivative, the third subderivative, and in fact the zeroth subderivative, which of course is just the same as the polynumber itself. So just for good reference, let's write down these various subderivatives that we computed. The zeroth one was the polynumber itself. There's the first subderivative, or just the derivative. There's the second subderivative, and there's the third subderivative. Now, for those of you who are not used to subderivatives and just think in terms of derivatives, what is the second subderivative in ordinary language? It's the derivative of the derivative divided by 2. So if you take the ordinary derivative of this and divide by 2, you get the second subderivative. And what's the third subderivative? It's the derivative of the second subderivative divided by 3. Take the derivative of this, divide by 3, you get the third subderivative. So if you just want to use differentiation, that's how you can go from one to the next. That's a simplified way of thinking about what the various derivatives are. All right, now let's look at the Taylor expansion at R. Now this is obtained by doing two things to the previous expression. The first is to interchange the roles of alpha and beta. So instead of expanding in powers of beta, we're now expanding in powers of alpha. We started with p of alpha plus beta. That's symmetrical in alpha and beta, so it's completely the same if we interchange the alphas and betas. And then the second thing that we do is that the betas, which are now appearing in each one of these things, are replaced with a number r. So we get that expression. That's d0 of p evaluated at r. Here's d1 of p evaluated at r. Here's d2 of p evaluated at r. And d3 of p evaluated at r. And now we make a shift or a translation. In this formula, we now replace alpha with alpha minus r. So let's translate. Then the left-hand side becomes just p of alpha. In other words, the original polynumber. And then the alphas, which are appearing here, here, and here, are replaced by alpha minus r. There, there, and there. And this is called the Taylor expansion of the polynumber p at r, because it depends on the number r that we've chosen. There's a different such expansion for every r. And this is a fundamental object because it's from this that we read off the various tangents to the polynumber, or to the polynomial. The first, well, the zeroth tangent is just the value of the polynomial at r. If you set alpha equal to r, then these terms all disappear and you're just left with that. The first tangent is the sum of the first terms all the way up to degree 1. The second tangent is the sum of all the terms up to degree 2. The third tangent, the sum of all the terms up to degree 3, which in this case is all of it. That's the general pattern of how we write down the tangents to the polynomial at r. We just take initial parts of the Taylor expansion. In other words, we truncate the Taylor expansion suitably. So let's have a look at what the tangent line and the tangent conic simplify to when we look at them carefully. So here are the first two terms in the Taylor expansion, the degree 1 part of it. What we want to do now is rewrite it. In other words, we want to expand it out and separate it into the things involving alpha and the things not involving alpha. So here are the things not involving alpha to begin with. And then we're going to have to add to that minus r times each of these. And have a look what happens when we take minus r times each of these. Minus r times b will exactly cancel with this br that's already there. So we'll have an a, but we'll have no brs left. Here there are cr squareds, and we're going to add to that minus 2cr for a total of minus cr squared. Here we have dr cubed, and we're adding to that minus 3dr cubed for a total of minus 2dr cubed. The coefficient of alpha is just this, so it's just copied unchanged. That is the tangent line to P at R. And here's our symbol for it. It's the first tangent to P at R. Okay, now we're going to look at the second tangent to P at R. We take the terms up to degree 2 in the Taylor expansion. So the first two terms here are just the ones we've already obtained, and we've already simplified that, so why not just take what we've already got, the formula for the tangent line, and replace it there. That's what this plus this is. So we only need to add this now to it. That's c plus 3dr, and here I'm expanding this out, alpha squared minus 2r alpha plus r squared. Now something pleasant happens. It's a little bit surprising that the thing becomes relatively simple. There's a lot of cancellation going on here. There's a little bit of magic trickling through. And the constant term is only a plus dr cubed. For example, this minus cr squared term that was there is going to be removed when we have an r squared times c here. So those two combine to get rid of that one. The minus 2dr cubed that we have there, well, that has to be combined with 3dr cubed there for a total of 1dr cubed. What about the coefficient of alpha? Well, here's how many alphas we have to start with, and then we have to add a certain number of alphas here. How many? Well, from here, minus 2cr alpha. That's exactly canceling this one. And also minus 6dr squared times alpha. We already have 3dr squared times alpha, so we're going to have minus 3dr squared altogether. And finally, the coefficient of alpha squared is the same as it is here. We're just copying this thing over. This is a polynomial of degree 2. It's called the tangent conic to P at R. There's a polynomial of degree 1. That's the tangent line to P at R. This is the tangent conic to P at R. And it's all just high school algebra. So I've just copied what we've already determined here. There's the original polynomial. There's the tangent line to it at R. There's the tangent conic to it at R. So for example, if the polynomial happens to be the one that we drew a picture of earlier, and if we're looking at the point r equals 1, then if you take this expression here, substitute a equals 5, b equals minus 3, and so on, and then plug in r equals 1, you can check that you get 7 minus 8 alpha. That's a line, and correspondingly, if you plug the various values into here, you get 6 minus 6 alpha minus alpha squared. That's a parabola opening downwards. And you can check, if you go back to that previous picture, that these are more or less the line and the tangent conic that I drew earlier. Let's make a nice little observation. We'll observe that if we're looking at the tangent line, its slope is just the derivative of P, evaluated at R. That's the same thing that we found for quadratic polynomials, that the slope of the tangent line is the first derivative, evaluated at the point in question. We see here that it's also true for cubics. In fact, it's true for any polynomial. The other observation is that the coefficient of alpha squared in the tangent conic sort of the corresponding top term here. That also has an interpretation in terms of a subderivative. That's the second subderivative of p evaluated at r. So in the formulas for the tangent line and the tangent conic, these terms are already dictated by the first and the second derivatives. These three terms here are perhaps a little bit less predictable, but make the subject sort of interesting. So that finishes our preliminaries having to do with calculus. Now I just wanted to say a few words about a special cubic, the simplest cubic, p equals alpha cubed. There's a graph of it. Sort of flattens out around 0. Of course, it increases rather dramatically as you keep going. And it has three important properties that it's worth pointing out. First of all, it's an odd function, meaning that if you evaluate it at minus r, you get minus what you get at p of r. So the value at minus 2, for example, which is minus 8, is related to the value of 2 by being negatives. 8 and minus 8 are negatives. That's obvious because minus r cubed is the same as minus r cubed. The second observation is that p is increasing. If r1 is less than r2, then when you evaluate, p of r1 is less than p of r2. That's perhaps clear if you just look at the right-hand side first. Okay, if you have two numbers r1 and r2, and r1 is less than r2, well, then if you multiply r1 by itself 3 times, you're going to get something less than if you multiply r2 by itself 3 times. So it's increasing in this side, and then by symmetry, or the odd property, it's also increasing on this side. In other words, as we go right, it goes up. And the third observation is that this is what's called a one-to-one polynomial. What that means is that if the polynomial's values at 2 points agree, in other words, if p of r1 equals p of r2, then in fact r1 equals r2. Which is to say that the function never takes on the same value at different points. So this is often referred to in terms of a horizontal line. If you have a horizontal line, then it may or may not meet the graph, as it turns out. But if it does meet the graph, it only meets it at one point. Right? It's not the case that there's a point there and another point there on the graph. The polynomial is one-to-one. Okay, so with these preliminaries, here is the prettiest theorem in calculus as far as I'm concerned. Let's see if you agree. So we'll give this theorem a name, call it the cubic disjoint tangent conics theorem. It's a rather long-winded name, but it pretty well tells you what the theorem says. It says that the tangent conics of a cubic polynomial are all distinct. And in more detail, that means there is no point xy which lies on more than one tangent conic. So tangent conics never meet. We have a tangent conic at every point on the curve. So for every point on the curve, there's a parabola, or perhaps sometimes a line in a degenerate case. But typically a parabola opening either downwards or opening upwards. So if we plot a lot of those quadratic polynomials, the tangents at a whole number of different points, we're going to find that there's no overlap whatsoever between any of those quadratics that we've drawn. No matter if we draw a billion of them, none of them overlap. Okay, here's a proof. The proof is short and sweet. Suppose P is, as before, our usual polynomial a plus b alpha plus c alpha squared plus d alpha cubed with d not equal to 0. And suppose that we have some point xy lying on some tangent conic associated to the point r. Well, here's the equation for the tangent conic, and if xy lies on it, it means that y equals this quantity plus this quantity times x plus this quantity times x squared. This, is, after all, is the equation of that tangent conic that we wrote down before. So it's all contained in this equation here. Let's have a good look at it. So what we're going to do is we're going to put all the terms involving r on that side and all the other terms on this side. So there's a y, the a comes to the other side, the minus a, the bx comes over here, the cx squared comes over here, and this term I'll explain in a minute. On the other side, we have dr cubed. In fact, all these three terms on our left will have a factor of d, so we'll pull that out. Then we'll have an r cubed, a minus 3r squared x, a plus 3rx squared, because we pulled the d out front. And at this point, we recognize, or should recognize, this is almost a binomial expansion of r minus x cubed. And to make it such an expansion, we add minus x cubed inside this bracket. So we've added minus dx cubed to this side, and to compensate, to keep things in equality, we're going to add minus dx cubed inside here. Well, then this is just dr minus x all cubed. And what's that telling us? It's telling us that the value of r, for which the tangent conic passes through xy, is given by this equation. This is some number. D is some number which is non-zero. So something equals r minus x cubed. But we just saw that the polynomial alpha cubed was 1 to 1. So there's at most one r that can possibly have this property. There's at most one value of r such that this thing cubed equals this number divided by d. That means there's at most one tangent conic that goes through the point xy. You can't find two tangent conics going through x1, only one. The r is given by this equation, and that determines r completely. And that's the proof of the theorem. It means that through every point, there's at most one tangent conic going through that point. The surprising nature of this result becomes clearer when we look at an example, especially when we try to draw some of these tangent conics. So here's that cubic that we were looking at before, the one with equation 5 minus 3 alpha minus 4 alpha squared plus alpha cubed. And here is the formula for the tangent conic of this thing at r. So I'm replacing the a, b, c, and d with 5, minus 3, minus 4, and 1, and that's the formula that we get. Now for various values of r, you can sub in here and you're going to get different conics appearing. And I've graphed some of them, at least roughly here for you. Probably the most interesting and the most important one is actually the one that occurs right here at the point 4/3. 4/3 is an important point for this cubic. In fact, it's the most important point on the cubic. It's the inflection point. And that's exactly the point at which this second derivative is 0. So at which point the tangent conic becomes a degree 1 curve instead of being a degree 2 curve. So it means that for that particular value of r, this gives a line, and it's in fact that line there in green. So that's the tangent conic at 4/3, or the second tangent at 4/3. It's not really a conic, it's a sort of a degenerate conic. This is sort of a line of inflection of the curve. Now here are some other tangent conics. At the point 2, the tangent conic looks like this roughly. At 3, there's point 3. The tangent conic is this one roughly. At 4, it's like this. At 5, it's should be something like that. As we go on further, we get more and more parabolas in that region there. On the other side of the line of inflection, say at 1, which is just a little bit to the left of the inflection point, the tangent conic there is pretty close to being a line locally. It looks like that. Of course, it's part of a big parabola. Then at 0, the tangent conic looks like this, parabola opening downwards. At -1, it's like this. At -2, it's like this. And as we keep on going down, there are more and more parabolas inside here. So pretty well every point in the plane is approximately on one of these tangent conics. The tangent conics fill up the visible plane, at least approximately. And if you actually draw a more accurate diagram, it's a bit of a marvel to me that all of these curves can fit together in such a beautiful way. They're all tangent to the original cubic. They're all exactly tangent at different points, but they all miss each other just dramatically, and they all sort of snuggle together to form kind of a foliation, like a bunch of leaves or lines that fill up the plane but are curved. All right, so as far as I know, this is a new theorem. It's a little bit surprising to me that it's new. It's surprising that it's not well known, and I very well doubt that it's really new. It's impossible for me to imagine that 19th century mathematicians would not have discovered this at some point. But there are so many works that have been lost in libraries and in dusty tomes that, that maybe someday we'll have access to electronically, but currently they're still essentially buried to us. So it's a little bit hard to say for sure that something is new, but I think this theorem really catches one's eye and deserves attention. This is just a start to cubic curves, and I think it's a good place to introduce an important new family of objects. We're going to now talk a little bit about algebraic curves, with the idea of extending our idea of conics and cubics from this polynomial point of view to a two-variable point of view. So this is going to allow us to deal with much more general curves, and the question of how does one do calculus with more general curves is a very interesting one. Especially how do we do elementary calculus like we've been doing here? Do the techniques extend? If so, how? We're going to make a start on that next time when we have an introduction to algebraic curves. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.